Okay, so in the last class we had discussed about uh, time series. We had discussed about when our data is or whatever we are observing is not stationary, means but it is evolving with time. The patterns are not uh, static, but they are dynamically evolving in time, right? So let us start from there. Brief recap. Okay, time series like uh, wherever motion is there, right? Wherever velocity is there, just the static position is not enough to characterize certain class or phenomena. But the evolving pattern is important. For example, the fan is moving. If you just take one snapshot, it is just one angle, right? But if you take the consecutive next snapshot, it changes its position. From there, you can tell, okay, this is moving with this much speed. And if you want to find acceleration, then you take at least 3 snapshots, right? So this is simple physics, but here we are dealing more with data which is showing different kinds of patterns. Another example could be weather record. Weather record means I want to forecast, let's say, tomorrow's temperature based on all the past history until today, right? Or I want to forecast whether it will rain or not. It's a discrete variable, right? Discrete random variable. Will it rain or not? But temperature was a continuous variable, means what will be the temperature tomorrow. Okay. Similarly, in speech, I could have speech recognition. So just single spectrum won't tell you the whole word, right? To know the word, you have to see the whole evolution over time, right? Then videos also we discussed. If you just take single snapshot, it will not tell you about the movement, the motion. If you want to know whether the car is moving or not, or what gesture I am making by waving my hand or by doing some action, that you cannot tell from single snapshot. So the temporal data is involved, means the dynamic evolution is important to characterize the class. Okay, to model the no. I think I messed up something. The order of the slides. Let me correct it. Okay, so let us work with some example. Okay, this is the example. Uh, Estimate the temperature on a day, let's say nth day, which is let us say tomorrow. Estimate the temperature on nth day, given the temperature on all the previous days, means n minus 1, n minus 2, so on up to whatever you want. And you have to estimate temperature at and on the nth day. How can you? What are the different approaches you can use to solve this problem? I have given you data, means whatever you want, I've given you. But now I'm asking you, can you please predict tomorrow's temperature? Let me write down what all approaches you suggest. Okay. Yeah. Polynomial regression, very good. So what will your regression model be? You will be estimating temperature n is equal to summation over some wk, temperature n minus k is 1 to whatever is your model size, it's a capital K, right? Plus you will add a bias, let's say W0, right? Is this a good model? Should be. Okay, so I can choose my order of K. This has a standard name in signal processing literature. What is that? Forward pass. Maybe you know better. I don't know. It might be, I'm not sure. Feed forward. No. Okay, feed forward neural network I have heard of. So this is called auto-regression model. It's regressing on itself, right? Or no. It's called moving average model. Okay, moving average model, weighted average of previous entries. Okay, so this is one regression. And any other suggestion? What would you like to use? Any classifier? Neural network. Regressor. Neural network regression you can use. Yes. Yes. Neural network. So this is basically a linear regression, and if you make it non-linear, then you can use neural networks. What else can you use? Something fundamentally different. Probabilistic models, right? You need not estimate a point estimate. You can give a distribution, Bayesian models. If I can tell probability of Tn given Tn minus 1 so on up to Tn minus k. This is a probabilistic model, right? I can use Gaussian mixture models or something. Okay, so this is okay. So I am going to discuss. Okay, just an overview. You have already told a deterministic model, like T is a function of previous time instants or previous temperatures, and as you suggested, linear models. A probabilistic model also could be used, as we just now discussed. So, okay, how many? Oh, okay, this will be a different exercise. Let us say I consider the deterministic model written over here. How many number of learnable parameters are here? How many learnable parameters are here? Tell me. K plus 1, very good. So this means if I want to increase my K, which means if I want to make use of more information from the past, then my model will increase linearly with K, right? Okay, let's discuss this model. Okay, neural networks. How about neural networks? Let us say I am using a neural network where the inputs are T n minus 1 to T n minus capital K, right? And these are my one hidden layer and one output layer. Let us say this is a regression model, so single Y, right? These are, so let us say there are NH hidden neurons. So if I increase my K, means what is how many learnable parameters are there in this model? And if I increase my K, what is the effect on number of learnable parameters? Pardon? Okay, let me, I'll write down. Somebody else should speak. These three boys, other than these three boys. Okay. Pardon? NH plus 1 into K plus 1, then that's it. Plus NH. Pardon? That's it. How many of you agree with this? How many of you agree with this? Okay, let us look at the first layer. The first layer, this one has the input layer has got K input nodes, plus one bias I can add, right? Plus one bias. Now, how many connections are there? This one connects to all NH of them, so means NH here. This one again connects to NH, so NH into K plus 1. So here we will have NH into K plus 1. And what about this connection? So here we have NH, and I will add one bias, let us say, right? Pardon? So this one will connect to 1, this one will connect to 1. So total how many? NH plus 1. So I will say plus NH plus 1. This is my answer. Okay. Okay. So this is the total number of learnable parameters. Now if I increase k, what is the effect on number of learnable parameters? If I increase k by 1, it increases by NH, right? Okay. So this means that I cannot keep increasing my number of previous data points which I want to make use of indefinitely. I have to put a limit. So that essentially is the idea of Markov model, right? You cannot make use of all the past information. To make your models small and easy to train, fast, manageable, you put a constraint. Okay, my current value depends only on past n number of values, right? Not all of them. Practically, it will depend on all of them, most probably. But you kind of model it. It's a model that you construct. Okay, assume that it is not depending on all of them. So let us say, look at the first equation. We have capital N number of observations, right? So you can write it like this, that your nth observation is dependent on everything starting from the first observation, right? And then n plus 1th will depend on everything until n. So the first equation, what is the assumption made here? In the first equation, what is the assumption made? In the first equation, so x1 to xn are random variables. What is the assumption made here? Somebody else? They are independent? Somebody else? The nth event won't depend on the past. It depends on the past. Huh? It depends on past. What is the assumption made in the first equation? Okay, there is no assumption made. This is general statement, simple product rule. So there is no assumption made there, right? It's simple product rule, that you chain rule or product rule, whatever you call it. So you kind of break down your joint distribution into conditionals. That is it, no assumption made there. In the next equation now, first order Markov chain. Here we have made an assumption that, okay, xn, when xn minus 1 is given, then xn won't depend on xn minus 2. So xn, if you know xn minus 1, then everything else from the past can be given up, can be ignored. This is an assumption. This is called the first order Markov model or first order Markov assumption, that you are assuming that your model, your current state depends only on the one past state, the previous state. But if the previous state is given, then everything else is unimportant, right? This is the first order Markov chain, and pictorially you can represent like this, that your x2 depends only on x1. On the other hand, you can have mth order Markov chain, which means the current value depends on previous m values, right? And if previous m values are given, then nothing else is required. Like values previous to previous m values, they are not required, right? And let us say for the second order Markov chain, you can represent it like this, that your x3 depends on x2 as well as x1. Okay, let us take this example. x4 depends upon x3 as well as x2. And if x3 and x2 are given, then x4 is independent of x1, right? Is this pictorial notation clear? Pictorially, you can understand that what are the dependencies. Pardon? Okay, so good point that P in the third equation you are saying, right? I have written that with k minus 1 non-existent means xk minus 1 means basically whenever you get x0 that does not exist, right? So it kind of you are kind of putting it out. Oh yes, that is correct. In the second equation it should start from 2. Let me correct it. Yes, thanks for pointing it out. Yes. So basically this is not a standard notation. I wanted to save my own time, so I wrote it like this because I can write m terms, but just to save time I wrote it like this. Okay, examples. First order Markov chain. Probability of temperature on a given day n. I can say my temperature at on the nth day, if n minus 1 is given, then everything else can be given up. Everything else can be omitted or ignored. So temperature at nth time, the probability distribution only depends on the temperature at n minus 1. That is it. Similarly, so now temperature is a continuous variable, right? I can do it with discrete random variables also, like rain. Probability of rain. Will it rain tomorrow? Yes or no? It depends on the probability of rain, means whether it rained today or not, whether it rained yesterday or not, like it can depend on n number of days. But the first order Markov chain will say the probability of rain tomorrow will only depend on the probability of rain today. And if probability of rain, if today it has rained, then the tomorrow's probability is fixed, no matter whether it rained yesterday or not. Right? So probability of rain on a day n depends only on rain at n minus 1. Okay. So this is called the first order Markov chain. Now, this is a gross assumption, right? That you are saying that my probability of rain tomorrow does not depend on probability of rain yesterday, or does not depend on the observation whether it rained yesterday or not. This is a gross assumption. So that's why. But are they really independent? No, actually they are dependent, but just that our model becomes very complicated if I try to include everything from the past. Okay. Now there is something intelligent which we can do to make them dependent, even while keeping our models small and manageable in size. You have read something about this, you have been reading something about this in the past, that is called latent variable models. By introducing latent variables, you can make your models very powerful, or you can give up the independence assumption while still maintaining your models small. Okay, so in general also we actually, in our normal day-to-day thinking also, we make use of latent variables often. For example, if somebody is able to answer the questions, we say, oh, there is a latent variable called intelligence which is making him answer the questions, right? So we try to assume latent variables, right? So similarly here, we can say our weather is dependent on season, let us say, a latent variable called season. And if it is summer season, my temperature will have this distribution more or less. If it is winter season, it will have this distribution more or less. Similarly, I can define different seasons, and I can say that my weather is affected by this latent variable and not by basically so, okay, let us look at this figure. This will help you to understand. Let us say X is my temperature, right? So, today's temperature depends on the season, and this season is inferred from previous yesterday's season, day before yesterday's season, right? N is the day here. So, season at nth day depends on the season of n minus 1th day. So, if I use this model, then I am not saying xn is independent of xn minus 1. But it is indirectly dependent, so through the season variable, right? So they are not independent, xn, xn minus 1, they are not independent, but they are dependent via this conditional variable called Z, latent variable. No, xn is independent of xn minus 1 given Zn, right? Given Zn. Pardon? Okay, what I mean to say is my xn is not independent of xn minus 1. Xn given Zn is independent of Zn minus 1, but not xn minus 1. This is what I mean to say. Right? So xn given Zn, it is independent of Zn minus 1, but it is still, you cannot say it is independent of xn minus 1. No, but mathematically they are not equivalent. Right? Intuitively you may think, but actually they are not. Because of these latent variables. So, okay. So, many times you may assume interpretable latent variables like temperatures, depends on season, like an interpretable latent variable. But many times you can also assume just statistically derived latent variables, like you did in the case of PLCA, NMF. Everywhere you assume latent variables which were kind of statistically derived. Even in case of k-means clustering, Gaussian mixture models, all your latent variables were statistically derived, right? By clustering, grouping. Okay. So similarly, you can derive here also if you don't want to do it in a supervised way. Okay. So this Markov chain property for the latent chain. Now my data is the observed data. So this dark thing represents observed data, and this white means which is not hashed. It represents unobserved, right? Latent variables are unobserved. So only observed things are made blue. So okay, so now my observed xn, which I call Tn here because of our example of temperature, my observed Tn, so this distribution, this probability of Tn given all the data, all the information up to Tn minus 1, including Zn. So this only depends on Zn, probability of Tn given Zn, that's it. So this is the Markov property of the latent chain. Oh, sorry, this is not Markov property, this is the conditional independence property. And here is the Markov property, which is, okay, my chain is Markov chain, first order Markov chain. My latent variable chain is a first order Markov process. But my observations are dependent via this equation. Okay. Is this clear? I think if you just keep this figure in mind, everything will be very clear that xn is independent of everything else given Zn, and Zn only depends on Zn minus 1, right? So given this, if you remember this figure, you will be able to understand things. Okay. Let us write down the joint probability of all these variables. Let's say I observed capital N cases. So probability of capital Nth observation, N minus 1th observation up to x1 observation, comma the latent variables, Zn so on up to Z1. I can write them like this. Okay. So in this way how I can write this? Okay, let me redo this thing. I can say this is probability of x capital N given Z capital N, comma everything else, right? Into probability of Z capital N given basically x capital N minus 1, comma everything up to x1, and then Zn minus 1, Zn minus 1, comma everything up to Z1, right? Similarly, then I can do for probability of xn minus 1 given Zn minus 1, comma everything. Okay, means this will, comma. But I know that xn given Zn does not depend on anything else. So I can write it like this. Xn given Zn, right? Similarly, I know this term, probability of Zn if I am given Zn minus 1, this term is given, then it does not depend on anything else. That is why I can write it like this. And in this way I keep going, right? Using my conditional independence property, I can keep expanding it. And ultimately, I can write it as a product form. My xn depending on zn and zn depending on zn minus 1, right? So this is a very useful thing to understand how we write the joint distribution. So my joint distribution is given by observation given the, if you go back to this one, so this observation given this latent variable, right? This latent variable given this latent variable, and then again this observation given this latent variable given the previous latent variable. In this way you are covering all the elements of your, basically all the random variables you are covering, and you are writing your joint distribution. Okay, and okay, again when you reach the final node, your pz1 given z0, because z0 does not exist, it will be simply pz0, sorry, pz1. Right? Any doubts until here? So we just discussed what is your model. It's a probabilistic model, which is it has a Markov property that things are evolving, but current state only depends on previous state, means just one step previous and does not depend on anything else given the one step previous state. And then it depends on, the observation depends only on the latent variable. That's it. Using this property, I constructed the diagram, and from the diagram I have written down the joint probability distribution. Okay, so this is true in general. So this kind of equation can be written for any nature of x as well as z. Now there is something which we have been doing very nicely, which is discrete latent variables, right? Where did we see discrete latent variables? Gaussian mixture model and EM algorithm. Yes, EM algorithm is for discrete latent variables. What else? Where else did we see discrete latent variables? K-means clustering. Where else? One more example I remember. PLCA. In PLCA we saw. Yeah. Okay. So HMMs, hidden Markov models, these are the models when my latent variable z is a discrete variable, right? So the same model which we wrote here, if my z is a discrete random variable, then this is called a hidden Markov model. So, but the observed variable could be either discrete or continuous, doesn't matter, but the latent variable must be discrete. That is a hidden Markov model. Examples of hidden Markov model. In weather forecasting, if you assume that z is a discrete latent variable, let us say season or something, or even statistically defined latent variable, discrete latent variable, then you can use a hidden Markov model to model your weather forecasting problem. Then speech recognition. What is the latent variable here in speech recognition? Okay, what is the observation in speech recognition? What do you observe? Words, no, you don't observe words. You have audio waveform. Your audio waveform is the observation, which you transform into a spectrogram, and then in the spectrogram you take individual spectra. These are your individual observations at different times or time steps, right? So your observations are those spectra or spectral magnitudes or whatever features you want to extract. And your what is the latent variable now in speech recognition problem? Okay, let us write down some examples. Okay, let me tell you, there is no single consensus that this should be the latent variable in speech recognition problem. It can be multiple things. So let me hear from you, what can you think of? Number of speakers. In speech recognition, you are trying to classify a given audio into words, let us say, words or sentences. So what will be your smallest unit which you would like to represent as a latent variable? Yeah, latent variable. Syllables. Yes, I can use syllables. So how many syllables are there in, let us say, English? No, English is not a good language. Hindi. No, yes, this is not my statement. This is the linguists say that English is not a good language to study grammar or phonology because it is so complicated. But okay, there are easier languages like Sanskrit or Hindi. So let us take an example from Sanskrit or Hindi. 30, 36, what consonants? 36 consonants or vowels? Okay. So when I write something like ka, kha, ga, these are all consonants. I think there are 5 into 5, 25, 25 plus a few. I think 36 maybe are consonants, right? And then 11 vowels. 36 consonants and 11 vowels. Okay. So when I write anything in Hindi like Kamala, or I write something with Matra, Hari. So here, how many syllables are there in Kamal? In Kamala, okay, because I'm using Sanskrit. Hindi has some problems. 3. In Hari. Okay, let me write it down in English, Roman script also. How many syllables are there in Kamala? 6 or 3 or something else? 3. In Hari, how many syllables are there? 2 or 4? 2. That is the beauty of Sanskrit, right? Each complete letter or complete unit, this akshara, that is the number of syllables. That is the smallest unit which you can pronounce. You cannot pronounce her, means this H. You need an A after that to be able to pronounce it. That is the syllable. Okay. But individual, okay, fine. It won't work. So how many syllables are there in Hindi? If there are, let's say, I'm not sure if there are 36 consonants and 11 vowels. How many syllables will be there? Pardon? Oh yes, you can say it is 36 into 11. But then there are half words also, like you can have what? Kashyapa. Okay, Kashyapa. Half sha, ya, and followed by an a. So this is one syllable. Right? So it's formed by half sha, ya, and a. Sha. Yeah, it will be huge number. So syllables is not a good choice to build your models because number of latent variables will be so huge. You will be kind of drowning in ocean of latent variables. So plus I'm just putting dash. Okay, other options could be some people who are too much data driven, who don't care how much data we need to train our silly models, they say consider each character in English as one unit. Like K will be one latent variable, A will be one latent variable, L will be one latent variable, H will be one latent variable. So you consider each character as your latent variable. So this means you will have 26 in English. It has its own problems. Same character can be pronounced in multiple ways, like C for cat, but C for chat is CH. C for cat and C for Ceylon. Ceylon, yes. Ceylon is C. Ceylon. Similarly, every character can be pronounced in multiple ways. So what do they do? What can you do to avoid that situation? Oh, okay. Stick to this character example first. Stick to the character example. We discussed something in the last class. We discussed something in the last class If individual unit is not sufficient, you have dependency on the context. What do? You expand it, right? You form n-grams. N-grams or units means you collect multiple units and make it one unit. It's called n-grams, or what else did we say? So basically, which means Kamala will have, let us say if I take 2 grams, Ka, Ma, Al, La, Kamala. Okay. So you will have these many 2 grams from. So total number of 2 grams will be. Total number of 2 grams will be for characters. 26. 26. Some of them might not be existing. For example, after Q you may not get an A. After Q always you get a U. So, but okay, those will be like some small number of cases. Ignoring that, roughly it will be of the order of 26 square. Okay, so that is single unit. Okay, there are many possibilities. Then phonemes are there, which are more linguistically oriented, and we can discuss that in some speech course probably. Okay, in video classification, I can assume the latent variable as my gesture. If I am waving my hand or I am saying please come, like, right? So I can use that as my latent variable. Okay. Let us consider the joint distribution. So this thing we have already seen. Now we break it down into 3 parts. So we have probability of Z1. Let us say I am sitting in Z1. Okay, let me draw actually the figure which I asked you to memorize. This is Z1 and this emits something called X1. Then you go to Z2, another latent variable. It emits something called X2. In this way you keep going. So I can say probability of Z1 into probability of Zn given Zn minus 1 into probability of Xn given Zn, right? Now, looking at the nature of these 3 kinds of probabilities, I can study them individually or separately. For this discussion, consider the example that let us say Xn is a random variable, but it is a real number, right? Temperature is a real number. X belongs to R and it is temperature on a given day N. And Zn is a discrete random variable. It can take 6 values because there are 6 seasons in India. If you go to US, you will get 4 values, but in India you get 6 values. So there are 6 seasons in India, so we get Zn is a discrete random variable with 6 different values possible. Okay. Now let us look at the first thing, which is probability of Z1, right? Probability of Z1. I don't have any Z0, therefore it is the starting point. Initial state probability. How do I model it? How do I model probability of Z1? Z1 can have 6 values. So probability of Z1 can be simply 6 numbers, right? Probability of Z1 equal to 1, Z1 equal to 2, Z1 equal to 3, Z1 equal to 6. These can be 6 numbers which sum up to 1 and they are greater than 0, right? This is one way to, and this is I think the most general way to store the value of PZ, probability of Z1. Just save these numbers. So what is the number of unknown parameters now? Capital K, the number of trainable parameters, capital K, for this part. Let's go to the next part, which is transition probability. How would you model that? Transition probability. Pardon? Z2 given Z1? Pardon? Equal to some A, yes. So you can model that also because there are, how many total number of values will be there? Because there are finite number of possible.
6 PP. Permutations of these. Permutations because they are directed. Probability from 1 to
Yeah, winter to winter also, because today is winters, tomorrow also can be winters. K square, yes, K square. It is K square. Okay. So basically, it is a matrix of K cross K, where you go from, let us say my previous state was J, and I move to K, then AJK. Pictorially, if I want to represent, there are two ways to represent this pictorially. One is, okay, I have got Zn minus 1, which transitions to Zn, right? But I can also make it in terms of individual values. So this is my Zn minus 1. It can have values k equal to 1, k equal to 2, so on up to k equal to capital K. And similarly, Zn can also have all these values, right? So what are the possibilities now? Let us say initially I was in k equal to 1 state and I moved to k equal to 1 state. Or I can go to k equal to 2 state. In this way I can go to any state including k equal to k state. Right? So how many transitions are possible? Capital K. And for each of these will be capital K. So means capital K into capital K. That is the size of my matrix. If you remember the neural network notation, it's exactly the same, right? You had WJK, here you have AJK. Here AJK is just a transition probability that you go from jth state to the kth state at the next time instant. Clear? Third, now the third term remaining is, okay, see this third term is probability of the observation given the hidden state. If I tell you the season, what is the distribution of temperature? So what model can you use? How will you save this? How can you model this? Huh? I have given you which state you are in. I have given you the Zn. See, Zn is given, and I'm asking you what is the distribution of the observation Pxn. Xn. Gaussian. Huh? Mean shifted Gaussians. Okay. So you are saying that we can model Pxn given Zn, or it should be a mean shifted Gaussian, right? The season is? Okay. So, okay, let me go back one step. Let me go back one step to previous examples. When I modeled PZ1, what was the assumption I used? There was no assumption made. It was a general case because you have finite number of Z1s. So I said, okay, assign individual probabilities and model them individually, and you get k values to store. And this was a general model, no assumption made, but apart from the Markovian property and everything. So model is fixed, but to model is fixed, but to model PZ1, I did not use any further assumption, right? Similarly, for PZn given Zn minus 1, I did not use any assumption. It was the most general case. Now I am asking, to model Pxn given Zn, what assumption or what is the most general model I can use? Pardon? X is a linear combination of Z's. Huh? Okay. Let me go back to Japanese answer. Bias. Okay. So if you say my Px given Z is a Gaussian distribution whose mean is given by Z's, is that the most general case? Is that the most general case? Yeah. Yes. So coming back to Nishant's point, yes. We can model it with any distribution. Why only Gaussian? It could be Laplacian. it could be uniform, it could be multimodal, it could be some non-standard form.
That would be depending on the smoothness of feed system.
Pardon?
Which model feeds best? We have to try different.
Yes. So basically, it has to be learned from the data. But what is that parametric form or the general form which you are assuming for P is x given z? Okay, let me. So for emission probability means probability of x which is observed given the z which was unobserved, the latent variable. Lot of options are here. If x is a discrete random variable, then we can use a matrix. That is the most general case, right? If x is also a discrete random variable, if I ask you whether it will rain tomorrow or not, given the season, right? How many possibilities you can have? If it is summer season, probability of raining and not raining. Winter season, raining or not raining. Finite number of sets, finite number of possibilities, which means total number of x, total number of values what x can take into total number of values what z can take. That is it. So if x is a discrete random variable, then using a matrix will be most general case. But if x is a continuous random variable, then we can use different models which are not the most general ones, but some assumption is involved. Like any standard PDF, for example, Gaussian mixture models or simple Gaussian models with their means equal to linear combination of z. Okay, anything you can use. But the point is that to make our model simple, tractable, we use standard PDFs. Okay. Or I can use any regression model. I can use a deep neural network, in which case my output won't be a distribution, but it will be a point estimate. Neural network won't give you an estimate, won't give you a distribution. Neural network will give you one estimate of your output, right? Which is also fine. People do use deep neural networks, and they are more popular than anything else. Okay, I think with this background, we can now, in the next class, we'll discuss the more mathematical details, like what can we do with this kind of a model, right? Thank you.